Monte Carlo Simulation is like playing a huge number of what-if games with a random dice roll each time. In decision modeling, we replace uncertain numbers, future sales, costs, prices, etc., with random draws from their possible ranges. By repeating the model thousands or millions of times, we build a picture of the whole distribution of outcomes, instead of a single best guess number. This helps managers see not just the average profit, but also the chances of very good or very bad results. The core idea is simple: repeat, random input, compute output, collect results. The name comes from the famous casino in Monte Carlo, where outcomes are inherently random. Every uncertain input needs a probability distribution that describes how likely each possible value is. Think of it like a weather forecast. Temperature might be normally distributed around a mean, while demand for a new product could be triangular because we only know a minimum, most likely, and maximum. Choosing the right shape normal, log normal, beta, uniform, etc., and estimating its parameters mean mu, standard deviation sigma, shape parameters alpha, beta, etc. is crucial. For example, if monthly sales are believed to average 10,000 units with a 20% variability, a normal distribution n 10,000 2,000 squared might be used. But if sales cannot be negative, a log normal or truncated normal is safer. Parameter estimation can come from historical data, sample mean, sample variance, or expert judgment using the three-point method to derive a triangular distribution. Computers cannot generate truly random numbers, but they can produce pseudo-random numbers that behave like random draws. The most common engine is the linear congruential generator, LCG. X sub n plus 1 equals a x sub n plus c modulo m, where a c and m are carefully chosen constants. Modern languages use more sophisticated generators, Mersenne twister, that have a very long period. Once we have uniform random numbers u tilde uniform 0 to 1, we transform them to the desired distribution. The simplest method is inverse transform sampling. If f inverse is the inverse cumulative distribution function, CDF of our target distribution, then x equals f inverse of u has that distribution. For a normal distribution, because there is no closed form inverse, we use approximations such as the Box-Muller transform or the ziggurat algorithm. This step turns the raw dice rolls into realistic input values for the model. How many dice rolls simulations do we need? Too few and the result is noisy, too many and we waste time. A common rule of thumb is to start with 5,000 to 10,000 runs and check the stability of key statistics, mean, standard deviation, percentiles. Convergence diagnostics compare results from successive batches. If the change in the mean is less than a preset tolerance, for example 0.5%, we consider it converged. The central limit theorem tells us that the sampling error of the mean decreases as 1 over square root of n, where n is the number of runs. Thus, the half-width of a 95% confidence interval for the mean is roughly 1.96 sigma over square root of n. If we want the error to be within $10,000 on an NPV estimate with sigma approximately $100,000, we solve 1.96 times 100,000 divided by square root of n less than or equal to 10,000, which gives n greater than or equal to 1.96 times 10 squared, approximately 384 runs. In practice, we use larger n to cover the tails of the distribution. After the simulation finishes, we have a list of output values, for example NPV. The expected value, also called the mean, is E of x equals 1 over n times the sum from I equals 1 to n of x sub I. The variance measures spread. Var of x equals 1 over n minus 1 times the sum from I equals 1 to n of x sub I minus e of x, all squared. Standard deviation is the square root of var of x. To express uncertainty, we construct confidence intervals. For the mean, we use the t-distribution if n is modest, otherwise the normal approximation. Ci 95% equals e of x plus or minus 1.96 times sd over square root of n. For percentiles, for example the 5th and 95th, we sort the simulated results and pick the values at positions 0.05 times n and 0.95 times n. This gives managers a clear picture, such as there is a 90% chance the NPV will be between $2 million and $8 million. In capital budgeting, NPV and IRR are the usual decision metrics, but both become random when inputs are uncertain. For each simulation run we compute, NPV sub I equals the sum from t equals 0 to t of CF sub t, comma I divided by 1 plus r to the power t, where CF sub t, comma I are cash flows drawn from their distributions in run I and r is the discount rate, often the firm's hurdle rate. After many runs, we obtain a distribution of NPV values, allowing us to answer questions like what is the probability that NPV greater than 0. For IRR, we solve for the discount rate that makes the NPV of each run 0, often using a numerical root finder. The collection of IRR sub I values yields an IRR distribution, which can be summarized by its median, mean, or probability of exceeding a target return. This approach replaces a single-point estimate IRR with a risk-aware picture. Many business variables move together. For example, oil price and electricity cost are positively correlated. If oil spikes, electricity usually follows. Ignoring correlation can underestimate risk. Copulas are functions that couple marginal distributions into a joint distribution while preserving each marginal's shape. A common choice is the Gaussian copula. We generate a vector z of correlated standard normals using the Kolsky decomposition of the correlation matrix sigma. Find lower triangular L such that sigma equals L times L transpose. Then set z equals L times u, where u is a vector of independent standard normals. We then transform each z sub j through the inverse CDF of the desired marginal to obtain correlated inputs x sub j equals f sub j inverse of phi of z sub j. Phi is the standard normal CDF. This technique lets us keep, say, a log normal demand distribution and a normal cost distribution while imposing a 0.6 correlation between them. After the simulation, we often want to know which inputs drive the most risk. Sensitivity analysis quantifies this. The simplest is the one-at-a-time approach. Vary each input by plus or minus 10% while keeping others at their base values and observe the change in the output statistic, for example mean NPV. Plotting the absolute changes as horizontal bars yields a tornado chart, with the longest bars indicating the most influential variables. A spider radar chart can display how the output percentiles 5th, 50th, 95th shift as each input moves across its range, providing a visual of upside versus downside risk. More advanced methods include regression-based sensitivity, partial correlation coefficients, or Sabal indices, which decompose output variance into contributions from each input and their interactions. Typical MBA exam questions test conceptual understanding and practical ability. Example 1, a firm is evaluating a new product. Expected annual sales follow a triangular distribution with minimum 8,000, mode 12,000, maximum 16,000 units. Variable cost per unit is $15 normal, mu equals $15, sigma equals $2. Fixed cost is $2 million. The discount rate is 10% over 5 years. Use Monte Carlo Simulation 10,000 runs to estimate the probability that NPV greater than 0. A solution steps. A. Define distributions and parameters. B. Generate 10,000 random sales and cost draws using inverse transform triangular and normal generator. C. Compute yearly cash flow equals price times sales minus variable cost times sales minus fixed cost. D. Discount cash flows to get NPV sub I. E. Count runs where NPV sub I greater than 0 and divide by 10,000 to obtain probability. Provide the numeric answer and a brief interpretation. Example 2. Explain how a Gaussian copula with Kolsky decomposition can be used to model correlation between oil price and electricity cost in a Monte Carlo NPV analysis. A solution. A. Estimate marginal distributions, for example log normal for oil, normal for electricity. B. Build correlation matrix, for example 0.7 correlation. C. Perform Kolsky decomposition to obtain L. D. Generate independent standard normals U. Compute Z equals L times U. E transform Z sub J via each marginal's inverse C D F. F use these correlated draws in the NPV model. Emphasize that the copula preserves marginals while imposing the desired dependence. These structured approaches show the student can translate business uncertainty into a